Hello friends, welcome to engineering tutorial. So far we have discussed around two questions related to signal flow graph, that is determination of the transfer function of a system using signal flow graph. So in this video we are going to discuss two concepts. First, the conversion of the block diagram into signal flow graph, and then we'll determine the transfer function of that signal flow graph. I have already discussed the basic concepts related to block diagram to signal flow graph in a separate video. You can check out that. So please see that video and then watch this video in order to understand it in a better way. So here we have to determine the transfer function of this given block diagram, but we are not going to use the block diagram reduction method, but we are going to use the signal flow graph method. So first we will convert this block diagram into signal flow graph, and then we'll determine the transfer function using Mason's gain formula. Okay, so first, the basic concept related to block diagram to signal flow graph, which states that the signal flow graph, it is actually a graphical representation of the block diagram. The nodes in the signal flow graph, they are either the summing points or the takeoff points. These are takeoff points and these are summing points. So these are these summing points and takeoff points constitute the nodes in the signal flow graph. So here we will represent each of the summing points and takeoff points as a separate node. Let this summing point be node 1, this summing point be node 2, this takeoff point here be node 3, this takeoff point be node 4, this summing point be node 5, this takeoff point be 6. Another critical point here, there are two ways in which we can approach a situation where there is a takeoff point immediately after a summing point. You can either take both of these summing point and takeoff point together as one node, or you can take them as two separate nodes. I generally take them as two separate nodes to avoid confusion. Okay, so here we have taken this summing point and this takeoff point as two separate nodes. Okay, so and then the output node here CS, and here the input node is RS. So let us draw the signal flow graph. Okay, we have R, then we have node 1, then we have node 2, then we have node 3, then we have node 4, then we have node 5, then we have node 6, and then we have C, the output node C. Okay, now let us determine the gain of the branches. In between 1 and 2 there is unity gain, so 1 and 2, the gain of the branch is 1. Between 2 and 3, node number 2 and 3, there is a forward gain of G1. 2 and 3, there is a forward gain G1, and then there is a negative feedback path with gain H1. So there is a negative feedback path between 3 and 2. Okay, so 3 and 2, there is a negative feedback path with gain, this 3 and 2, there is a negative feedback path with gain minus H1. Okay, then between 3 and 4 there is a forward gain of G2. So here 3 and 4, there is a forward gain G2. Okay, then between 4 and 5 there are 3 forward paths with gains G3, G4 and G5. Okay, here we will do the same. 4 and 5 there is G3, there is G4 and then there is G5. Then between 5 and 6 there is unity gain. As I have taken them as two separate nodes, there is unity gain. Between 6 and output node C there is a gain of G6. Between 6 and C there is a gain of G6 output node. Okay, so the signal flow graph is done. No, there is another feedback path. See, there is another feedback path between this 6, node number 6 and 1. Negative feedback path with gain H2. Okay, this minus sign in the summer, it means there is negative feedback connection between node 6 and node 1. Okay, so let us draw it. Node 6 and node 1 with gain minus H2. Okay, gain minus H2. Okay, so the signal flow graph is done. This is the signal flow graph. So signal flow graph we have drawn. Now we will use this signal flow graph to determine the transfer function C by R using Mason's gain formula. Okay, so we converted the block diagram into its equivalent graphical representation. So this is the signal flow graph equivalent of the block diagram which was given in the question. Now we have to calculate the transfer function of the block diagram, that is the signal flow graph, using Mason's gain formula. Okay, so as I have already discussed in the previous two questions, the Mason's gain formula, the transfer function output by input is given by the product of the individual forward path gains and path factors divided by the graph determinant. Okay, so first we have to determine the forward paths, the forward path gains P1, P2, P3 up to depending on the number of forward paths. Then we have to determine the path factors and then the graph determinant. Okay, so first the forward path. The basic definition of a forward path, it says it is a collection of branches starting from the input node to the output node in the forward direction with no node being repeated. Okay, it is a collection of branches connecting the input and output node in the forward direction. Okay, so let us see how many forward paths are there in between the input and output node. So the first obvious forward path is this R1, 2, 3, 4, 5, 6, C along G3, this G3 branch. So this is the first forward path. Always pay attention to the direction of the arrows. So the first forward path is P1 R1, 2, 3, 4, 5, 6, C. Okay, this is the first forward path, and the gain is the product of the gains of the individual branches. So here it is 1 into 1 into G1 into G2 into G3 into G6. So it is G1, G2, G3 and G6. Next, the next forward path is the same until node 4, that is R1, 2, 3, 4, but we have to proceed in the direction in the branch G4. See, this is also a forward path. The direction of the arrow is in the forward direction. So along G4, then 5, 6, C. R1, 2, 3, 4, 5, 6, C. The nodal representation will be the same as forward path number 1, but the direction will be along the branch G4. So the nodal representation will stay the same, that is R1, 2, 3, 4, 5, 6, C, but the gain will be different, G1, G2, G4, G6. Okay, here it was G3 in P1, here it is G4 as it is along G4. Next, forward path number 3. See, same until 4, that is R to 1 to 2 to 3 to 4, but here we'll move along this lower branch G5, the forward lower branch G5. Okay, then 5 to 6 to C. So the nodal representation will be the same as P1 and P2 are 1, 2, 3, 4, 5, 6 and C, but the gain will be different. There is G1, G2, G5 and G6. So every change happens in between the nodes 4 and 5, as there are 3 forward paths in between nodes 4 and 5. So all the different forward paths are created in between these two nodes 4 and 5. Okay, now we have to determine the number of loops. Okay, the number of loops. So the first loop, so the loop, what is a loop? The basic definition of a loop, it says it is a closed path in between two nodes, that is it starts and it ends at one node. It is a closed path, that is it is a collection of branches which start and terminate at the same node. It starts and ends at the same node. It is a closed path. So the basic technique to determine a loop is focus on a particular node if it has both incoming and outgoing arrows. See this node, it has an outgoing arrow and an incoming arrow, so it has a loop associated with it. Okay, it has a loop associated with it. So the loop L1 is from 2 to 3 to 2, back 2 to 3 to 2, and the gain of the loop is simply the product of the gains of the individual branches involved in the loop. So it is G1 into minus H1, which is minus G1 H1, the gain of this loop. The second loop will be, see this node 1, it has one outgoing arrow and one incoming arrow, so it has a loop associated with. Now see, it will be interesting. One loop will be 1, 2, 3, 4, 5, 6 and again back to 1 along G3. This will be one loop. Again another loop will be 1, 2, 3, 4, 5 along G4 to 6 back to 1, and the third loop, there will be another loop which will be along G5. So same 1, 2, 3, 4 until 4, this will be along G5, G5 to 5 to 6 to 1. So the same way as 3 forward paths were created in between the nodes 4 and 5, because there are 3 forward paths, 3 forward branches present in between nodes 4 and 5, so that's why 3 forward paths are created. Similarly, here 3 loops will also be created in between 1 and 6 and 1. Okay, 1 2 3 4 5 6 1. In between these nodes 3 loops will be created because of these 3 forward branches. Nodal representation of each will be the same, that is, so let us write the nodal representation of L2, L3 and L4. Okay, the nodal representation is 1 2 3 4 5 6 and 1. The nodal representation will be the same, but the gains will be different. So for L2 it will be G1, G2, G3 into minus H2, so it will become G1, G2, G3 and H2. For L3 it will be G1, G2, G4, G1, G2, G4 into minus G1, G2, G4 minus H2, so it will be minus G1, G2, G4 and H2. And loop 4, the gain will be G1 into G2 into G5 into 1 into minus H2, again back to 1. So it will be loop 4 minus G1, G2, G5 into H2. Okay, so there are all total 4 loops and 3 forward paths. Now let us determine the path factors and the touching and non-touching loops. Okay, so first let us determine the touching and non-touching loops. So here it is easy, as loop L2, L3 and L4, they have the same nodal representations, so we can directly compare them. See, 2 loops are said to be non-touching. Okay, 2 loops are said to be non-touching if they have no common nodes in between them. Okay, if they have no common nodes in between them, 2 loops are said to be non-touching. But if they have at least one node common in between the 2 loops, then it is said to be touching. So here the nodal representations of L2, L3 and L4 are same, so it is very easy and quick to compare the 4 loops altogether. See, L1 has a nodal representation of 2 3 2. L2, L3, L4 have nodal representation of 1 2 3 4 5 6 1. So see, 2 3 2 3, there is a common node between L1 and L2, L1 and L3, L1 and L4. So all of these loops have 2 common nodes, 2 3, so they are all touching together. So there is no 2 non-touching loops, no 2 non-touching loops. So calculations will be very easy. No 2 non-touching loops. Now we have to determine the path factors. Okay, the path factor, what is the definition of a path factor? The path factor for a particular path, let's say for the kth path, is given by 1 minus sum of the loop gains of loops, sum of the loop gains of loops which the particular path has not touched, which the path has not touched. Okay, the loops which the path has not touched, the gains of that loops. Okay, so this is the definition of the path factor. Now let us see what is the path factor of P1, P2 and P3, that is delta 1, delta 2 and delta 3. Now similarly we have to compare the nodal representations of P1 with each of the 4 loops, P2 with each of the 4 loops and P3 with each of the 4 loops, as we did in touching and non-touching loops. See, the nodal representation of P1 is R1 2 3 4 5 6 C. The nodal representation of L1 is 2 3, so 2 3 2 3. So there is common node between P1 and L1. So P1 is touching L1. P1 has 1 2 3 4 5 6. L2, L3, L4 has also 1 2 3 4 5 6 1. Okay, So there is common node 1, 2, 3, 4, 5, 6. So P1 is touching both L2, L3 and L4. So the forward path P1 is touching all of the loops. So the path factor of P1, that is delta 1, is 1 minus 0 is equal to 1. All we have to do is find common nodes between the nodal representation of a particular path and the loops. If there is at least one common node in between the path and the loop, it means the path is touching that loop. So here we are finding common nodes between P1, L1, L2, L3, L4. So P1 is touching all the loops. Similarly, P2, the nodal representations are the same for P1, P2, P3. See, the nodal representation for P1, P2, P3 are same. So if P1 is touching all of the loops, so P2 and P3 will also be touching all the loops. Okay, please pay attention. The nodal representation of P1, P2 and P3 are the same. See, the nodal representation of P1, P2, P3 are same. So if P1 is touching all the loops L1, L2, L3, L4, it means by default P2 and P3 will also do the same. So no need to do anything. Our calculations got easy. So delta 2 is also 1, delta 3 is also 1. Now let us just put these values and determine the transfer function of the system. So now we'll determine the transfer function of the system using Mason's gain formula. So the Mason's gain formula again is given by summation of k equals to 1 to whatever the number of forward paths. So it is pk delta k, product of the forward path gain and the path factor, by graph determinant. So first we'll determine the graph determinant. Graph determinant is 1 minus sum of individual loop gains plus sum of gain products of two non-touching loops minus sum of gain products of three non-touching loops, and so on. So here we don't need this because there is no non-touching loops. So this part we can avoid. So 1 minus sum of the individual loop gains. So here it will be, we had already written the loop gains for all the loops. So you can rewind the video and note it down, and if you have noted it down already, please refer to that. So it will be 1 minus the individual loop gains L1, L2, L3 and L4, which will be minus G1 H1 minus G1 G2 G3 H2 minus G1 G2 G4 H2 minus G1 G2 G5 H2. This is the graph determinant. Okay, so now we'll just simply put this value in the denominator. We have calculated the graph determinant, and now we'll determine the transfer function of the system. So the transfer function of the given signal flow graph will be P1 delta 1 plus P2 delta 2 plus P3 delta 3 by delta. As there are three forward paths, so three terms will appear in the numerator. Now these are the forward path gains P1, P2, P3, and delta 1, delta 2, delta 3 are the path factors of the respective forward paths, which we have calculated the values earlier. So it will be P1 forward path gain P1 G1 G2 G3 G6 into 1, delta 1 is 1 path factor, plus G1 G2 G4 G6 into 1, then is G1, G2, G5, G6 into 1. The path factors of all the forward path were 1. Then this is 1 minus sum of the individual loop gains, the graph determinant which we calculated, which is 1 minus G1 H1 minus G1 G2 G3 H2, then minus G1 G2 G4 H2 minus G1 G2 G5 H2, total 4 loops, and there are no non-touching loops, touching loops, so there is no need to go any further. So we have calculated the transfer function of the above system. Here minus minus, it will become plus, in all these terms it will become plus. Okay, so we have determined the transfer function of the given system. So first it was given in block diagram form, we converted into signal flow graph using the conversion technique, then we used Mason's gain formula to determine the transfer function. So these questions can be a little bit lengthy, it can take up to 10 minutes. Here I am explaining a lot, that's why it's taking so much time, but if you practice it more and more, it can be completed in 10 minutes, 10 to 12 minutes, maximum 15 minutes it can be completed. Okay, so you just have to be quick to identify the loops, the forward paths, whether they are touching or not. So the more you practice, the more it will come to you. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.